Okay, ladies and gentlemen, the second speaker of this afternoon session is Dr. Nathan Baker. Nathan Baker is the director for the Advanced Computing, Mathematics, and Data Division at Pacific Northwest National Laboratory, and is visiting faculty member in the Brown University Division of Applied Mathematics. So Dr. Baker's today's topic is the scientific machine learning. So yeah, it should be very exciting, and then we can share a lot of the experience at your labs and beyond. Okay, thank you very much.
Thank you. And thank you as well to Manish, Satoshi, and others for the opportunity to present. I'm very much looking forward to this event. So I'd like to start by telling you a little bit about the goals for the talk, what it is and what it is not. So the primary purpose is to explain some activity that's been going on for about 2.5 years now that was sponsored by Department of Energy's Advanced Scientific Computing Research Office. So that's OSCAR, and we love acronyms, so you're going to hear acronyms the whole talk. But OSCAR set out through a charge by Barb Helen and under the direction of Steve Lee to try to understand what some of the gaps are in scientific machine learning, and in particular what some of the gaps are in being able to use machine learning alongside our existing tools for scientific discovery, including scientific computing and scientific data management. So that is kind of the first order of business. The second portion of the talk will describe a little bit of how Pacific Northwest National Lab, or PNNL, is pursuing and addressing those gaps, pursuing research funded by OSCAR, by other DOE sponsors, and by other sponsors in the US government. And then in the last portion of the talk, I'd like to describe some of the activities that have happened most recently through the AI town halls that have been sponsored by DOE to set the next steps in terms of machine learning. But first, I'd like to point out that very little of what I'm going to be talking about is necessarily my own research. I do research in scientific machine learning, but it's much more interesting to describe some of the other larger projects going on at PNNL and elsewhere, and specifically how they address these priority research directions and gaps that have been identified through the scientific machine learning workshop effort. So first and foremost, I would like to thank Steve Lee, who has been driving much of this discussion about scientific machine learning and its place in the OSCAR and broader DOE research portfolio. As I mentioned, most of the work I'll be talking about at PNNL has been funded by different parts of DOE, particularly OSCAR and BES, as well as the Exascale computing project, and then some work funded by Department of Defense through DARPA and DTRA. I'll have another slide where I go through the co-organizers of this scientific machine learning, or SCIML or SciML effort in more detail, but this was very much a group effort. Would not have been possible without the outstanding team that Steve assembled to make this happen. And then as I call out examples of how PNNL is addressing the research gaps in machine learning, you'll see several of these names throughout the talk. And then finally, I'm sure I forgot somebody. Apologies, there's lots of collaborations involved in this. Okay, so what is scientific machine learning? It's probably best by starting to describe what it is not. It is not an attack on machine learning that is unscientific. Whenever you say something scientific, it immediately applies. There's something else out there that's pedestrian or what have you. That's intent. It's also not new. One might argue that the community has been doing scientific machine learning ever since regression and related data analysis techniques or classifiers were applied to scientific data and scientific problems. So scientific machine learning in some sense is very old. But some of the questions associated with scientific machine learning have a lot more urgency due to the rapid growth in deep learning and related techniques. And that's what this workshop and some of the things I'm going to be describing to you was designed to focus on. It was designed to focus on that rapid rise and addressing the questions that we would need in order to make this triplet at the bottom here with OSCAR Applied Mathematics to make this triplet complete. What would it mean to add scientific machine learning alongside scientific computing and scientific data management? So that's what we mean by scientific machine learning. It's not a new term, and certainly the inverse of the term is not intended to be pejorative. So Oscar set out about 2.5 years ago under the direction of Steve Lee to try to understand what are the gaps in adding scientific machine learning alongside the standards of scientific computing and scientific data management. This followed a framework called the Basic Research Needs Framework. This is something that DOE Basic Energy Sciences pioneered several years ago, and it's an excellent way to bring the community together and explore a new research area with hopefully a community consensus-driven approach that will allow the community as a whole to understand, where does the research need to go next in order to address an important need, in this case, the need to make scientific machine learning trustworthy or a tool that can be used alongside the others that I just mentioned. So there's 2 links here. You can also find these links from the Oscar homepage. There's a fairly lengthy report, and I will say that the machine learning workshop took place in 2018. Some of the work leading up to that workshop focused on creating what's called a factual status document. That represented a snapshot of the field prior to that 2018 workshop. As soon as we hit compile on the LaTeX document, that was out of date. This field moves far too quickly for any document to stay current, so please keep that in mind. However, we feel that the questions that were outlined during the workshop and the questions that were presented in the report that was published in January of 2019 are still very current, very important, and critical to raising the visibility and reliability of machine learning to an area where we can use it alongside the other tools. So at the bottom, we have a list of the co-organizers. So I led the workshop along with Timo Bremer, with Yanis Kavrakidis, Eric Hegberg, Habib Najim, Stefan Wild, Manish Parashar, Karen Wilcox, Abani Patra, Jamie Sethian, Mark Ainsworth, Frank Alexander, and Jeff Hittinger. So it was really a great team that pushed this thing forward. And the workshop itself consisted of almost 200 people from a variety of different areas exploring this topic and putting their input into what the key gaps are. So what are the key gaps? You'll see this slide in a couple different forms. You'll probably be tired of this slide by the time the talk is done. So we've identified 6 priority research directions. These are the 6 research priorities that we feel will help address the issues that may prevent or further enhance the stature of machine learning as a scientific discovery tool. They're broken into 2 groups, and I'll go through each of those groups. And then, as I mentioned, I'll provide some examples of how we at PNNL are trying to address those gaps. So briefly, the first group focuses on the foundations of scientific machine learning. So what's needed to understand the core gaps and the core mathematical problems. And those involve domain-aware machine learning, incorporating domain knowledge, interpretability, which is a hot topic in many different areas, here with a specific scientific angle, and robustness, which again is a hot topic in many areas. And that's something that I hope you'll recognize throughout this, is that these aren't 6 unique, distinct things that only the scientific computing community would care about in terms of machine learning. These are themes that are popping up in other areas. They're themes that DARPA and other programs have funded research into, some of the themes you heard about in the previous talk from Lynn. So we hope that, as DOE focuses emphasis and attention and its researchers address these, it'll impact not only scientific machine learning, but also the broader community. The altitude is getting to me, so bear with me for a second. Okay, so the first question focuses on what we call domain-aware machine learning. And data-driven science, the discovery of new knowledge from data, is invaluable. It's one of the things that's made scientific machine learning so exciting and such a priority. However, data is not everything. We have centuries of scientific investigation and discovery that have given rise to both physical and empirical rules that help drive science and have reliably driven science forward, as I mentioned, for centuries. The question is how can we have our cake and eat it too? How can we put those 2 things together? And that's the notion behind domain-aware machine learning. How do we take the knowledge that we have about a domain, integrate it with a machine learning model, and in doing so, hopefully realize a few favorable outcomes? So these outcomes could include the simplest of, well, if I have a model that's already trained on what I know about a domain, does that mean I can use less data? Do I essentially move immediately into a reinforcement learning mode where the physics or the empirical knowledge that's been encoded in my model somehow gives me a leg up and reduces the additional data that I need to train the model? That's one question. A second potential benefit is robustness. If I am building in things that I know and expect from this model, then can that help regularize or manage the outcomes of the model? At a minimum, can it help me move away from solutions that might end up in unphysical domains that violate the knowledge that I built into the model? Avoid negative densities, avoid spontaneous leaping of systems from here to there in a phase space that violates laws of thermodynamics. So there's a hope that the regularization can occur as well. And there's many other benefits, some of which we'll touch on in the next priority research direction as well, of potential interpretability, efficiency, so on and so forth. But this is essentially the old saying of don't throw the baby out with the bathwater. As you're able to discover new knowledge through these data-driven techniques, make sure that you're doing so alongside the domain knowledge that you already have at hand, and therefore raising the important question of what are the mathematically robust ways to put those two things together? So I have an example here on the right, some work out of George Karniadakis' lab. I've included the citation at the bottom. You'll also hear a few additional examples from George's group, collaborations with PNNL and with others in the second part of this talk. Okay, the second piece is in some sense everybody's favorite, especially as we talk about deep learning types of models. So for those of you who, including myself, who love decision trees and support vector machines, you say, what do you mean? It's already interpretable. That's true. The problem is as you start to make deep models, you think about deep Gaussian processes, you think about deep convolutional networks, interpretability becomes much, much more of a challenge. However, scientific discovery is not just about building a better regression engine or a better classifier. It's about fundamentally increasing the knowledge that you have into a domain. And with that in mind, interpretability is an important problem and an important gap in scientific machine learning. Unless you can pull apart one of these models and you have somehow increased your knowledge of the system in doing so, you might argue that this is a fancy black box that helps you maybe guide your next experiment or perhaps do a better job fitting your existing data, but maybe isn't contributing to the overall understanding of the domain. So interpretability is critical. Now, interpretability, as I mentioned with all of these priority research directions, is being addressed in several different domains. I think the scientific domain is unique and in some sense maybe an easier challenge because of the issue of domain knowledge. If we have models that are aware to domain knowledge, if we have models that are incorporating domain knowledge in their function, then ideally we have models that can use that domain knowledge to help understand what's going on inside the machine learning engine. And that's the idea of this priority research direction. Now, along with it, there's other benefits that hopefully we can realize, not least of which is the notion of debugging. We're not just understanding the model for science's sake, we're also trying to understand the model from the standpoint of when it goes wrong. What are the limits of confidence we have on the model? And that'll pop up in subsequent priority research directions as well. So I'll move on to I apologize. On the right-hand side here, I included an example from researchers at Lawrence Berkeley Lab that have been using machine learning to essentially develop saliency maps to call out important parts of proteins associated with their function, their interaction with other molecules, and things like that. Okay, the third question is robustness. My background is chemistry and applied mathematics, and one of my favorite things to do with finite element solvers was prove that the techniques we were developing were well posed. That is, a solution existed, it was unique, and it depended continuously on the input data. It was wonderful, it was packaged, and it appears right now, anyhow, to be very, very difficult for many of the deep learning techniques that are being employed in scientific applications. So what is the equivalent set of robustness or well-posedness statements that we can make about machine learning tools? These are very important. These types of proofs, these types of guarantees are essential in how we use scientific computing tools to guide experiments, steer instruments, design materials, and other scientific undertakings. What does it mean here? we're already dealing with a nonlinear problem. So we can pretty much be sure that a solution, if it exists, may not be unique. We have to think about how we represent the problem in such a way that we can start to develop envelopes of robustness or guarantees that maybe work within the neighborhood of a solution, statements that may not be as strong as what we'd expect for a linear solver or the solution of a simple PDE, but still give us confidence in how these tools can be used when we're applying them to important scientific problems, or as Lynn mentioned in the previous talk, even broader problems on a societal level. So robustness and reliability probably do not require too much belaboring on this slide. It's an essential research direction. It's something that we have to have in order for these tools to be useful. And it's going to have to proceed on many different fronts, some of which will leverage all the knowledge that's been accumulated so far in the applied math and statistics community about nonlinear regression and the techniques that underlie some of these tools. Some of it, though, is also going to have to require new approaches to how we think about these nonlinear systems that are deep networks and how we represent them, how we think about uniqueness. So one simple example over here on the right comes from Sandia from the Combustion Research Facility. And it talks about how they've addressed the problem of robustness in turbulence modeling through their tensor basis neural network, and how they did so by trying to build in things like rotational invariance, enforce that in the model, and were able to show that they had much better model performance when those types of robustness constraints were built into the model. And of course, this touches back on domain awareness and many of the other issues I've talked about already. So those are the first three priority research directions. The second three focus on capabilities. In some sense, if the first three form the foundation of scientific machine learning, the next three talk about how to realize its potential in different scientific undertakings. Very briefly, these focus on the problem of scientific machine learning in data-intensive applications. They focus on using machine learning to enhance simulations, and they focus on using machine learning to guide and steer complex systems, including simulations, scientific instrumentation, and things like that. So I'll start with the data-intensive scientific machine learning. And this basically addresses the problem that the input data for any scientific undertaking are usually incomplete, almost always uncertain. The models that you have for the domain or your understanding of the domain may be equally incomplete and uncertain. And on top of that, most of these systems are extremely high dimensional. So when we think about modeling of these systems, we have to be thinking about approaches that can address all of those different degrees of difficulty in the underlying problem. So how do we do that? Well, thankfully, that's one of the areas where approaches like deep learning, approaches like deep Gaussian processes and things like that have really shown. And so this is an area where we think that it should be an early win for scientific machine learning. That being said, as we think about noisy data, incomplete data in the machine learning sense, we need to be thinking about it in the same way we think about noisy inputs and noisy parameters in the scientific computing sense, and that means uncertainty. It will be extremely important as we're using these methods to explore high-dimensional systems with uncertain inputs, that we have the tools that allow us to understand how uncertainty in the training data and uncertainty in the models translates to uncertainty and confidence in the quantities of interest that we extract for those systems. So at the same time that we open up the doors to hopefully being better able to understand noisy, high-dimensional scientific systems, we have to keep in mind the importance that has been, sort of part of scientific computing from the beginning of understanding uncertainty. So uncertainty quantification is not going away as we move to scientific machine learning. In some sense, the gauntlet's been thrown down for it to scale to a whole new set of very nonlinear systems and continue to show how to harness and bound the predictions that come out of these tools from very uncertain inputs. So over here on the right, we have some examples from Oak Ridge where they've shown how to sort of sift through high-dimensional, noisy data that comes from molecular simulations. These molecular simulation data is always incomplete. Ergodicity is a very difficult thing to prove, but they showed how they could use machine learning tools to basically understand and characterize this high-dimensional space and describe some of the key pathways for different protein folding events. Okay, I'll take an aside here and make an editorial comment about the next two priority research directions. The committee really wanted to call these inner loop and outer loop, because in some sense, machine learning for this priority research direction I'm going to talk about right now focuses on how to replace the inner core of scientific computing with a machine learning algorithm, while as the next one talks about how to put, whether it's complex models or instruments, surrounded by an outer loop of machine learning. We thought this was a wonderful idea. We thought it described the picture beautifully until someone showed us a picture of traffic on the 495 and other interstates around DOE. And that was the end of that. We really did not want to associate these priority research directions with DC Beltway traffic. So instead, we have the names we have. But the key ideas are still the same. And this one is all about how can we take advantage of the things machine learning does. Whoops, I think I lost audio there for a second. Take advantage of the things that machine learning does well and use it to speed up or regularize, somehow make more robust the core ingredients of a scientific computing algorithm. So these could be things like if we only need a few eigenvalues of an operator and we know the inputs are noisy, then perhaps we can do better by trying to estimate those eigenvalues or fit them using some sort of deep neural network model. The example on the right comes from Livermore, where they showed how they could dramatically improve adaptive moving mesh methods in finite elements by building in machine learning tools that helped understand and predict when elements were about to invert or become degenerate and cause instability in the overlying algorithm. And this is very much the spirit of this technique, of this priority research direction. Trying to understand when scientific computing techniques have elements that would be amenable to substitution by new machine learning methods with the idea of somehow making the overall approach more robust, speeding it up, making it more efficient, whether it's from a power standpoint or a data standpoint or any other of the aspects you might care. So this is the inner loop, not to be associated with 495 or any other beltway priority research directions. The second one here is the outer loop, or the notion of intelligent automation or steering for complex processes. Now, complex processes and systems appear in a variety of different contexts. We've been talking about scientific computing, so it's probably useful to stick with that theme and continue to talk about how to steer a complex scientific simulation or computation. But there's plenty of other cases where you can imagine these tools being useful. And again, at the risk of boring you with repetition, many of these priority research directions map not only to the key needs of OSCAR and its associated communities, but they touch on many other areas as well. So this one asks the question, if I have complex instrumentation or I have a complex simulation, how do I bring in some form of machine learning or artificial intelligence to help steer that calculation or that complex system into regions that are going to be most useful for obtaining the results that I want? Excuse me. So this again opens up a variety of research questions, not least of which is, well, what are the right techniques to use there? What are the approaches that can be used for complex control under uncertainty and noise? I emphasize that phrase because this isn't necessarily a new problem. Control problems under noise with machine learning assistance have been explored for a long time. The question is finding the right techniques, matching them up, and understanding how to use them for scientific instrumentation and scientific computing. And so this example on the right is from Prabhat at Lawrence Berkeley Lab, and it talks about how to do this in the case of a different complex system, network controllers. So it's not a scientific simulation. In some sense, it's a big extended facility or instrument. And how can the control aspect of this system be augmented by machine learning techniques to help optimize its performance for different types of applications? Okay, so those are the 6 priority research directions. If you fall asleep now, hopefully you haven't fallen asleep yet, you will have gotten the most useful part of the talk, which is basically saying these are 6 areas we need answers to. These are 6 gaps that we need to fill in order to bring scientific machine learning to equal status alongside scientific computing and scientific data management. In the next few slides, I'm going to give a few examples from Pacific Northwest National Lab, from PNNL and its collaborators, where we've tackled a few of these PRDs, and I want to, these priority research directions. And I want to just use these not as in-depth vignettes, but more as just sort of small examples of what specific solutions, not the only solutions, not complete solutions, but specific initial steps in the direction of these priority research goals might look like. So I'm going to start with two examples from domain-aware machine learning. And these hit on the two sides of domain awareness that I mentioned earlier on. A lot of scientific knowledge, and I don't want to get into an ontology discussion here, but a lot of scientific knowledge can be roughly lumped into empirical knowledge, where we learn rules about how the world around us works, often for very complex systems where writing down a conservation law doesn't make sense. Medicine isn't at the level of a Euler-Lagrange system that we can minimize and say, hey, look, it's the PD that describes human disease. So empirical knowledge is important in a wide range of domains. At the same time, physical models have been extremely useful for scientific discovery and for making progress in a wide range of problems. So if we think about domain-aware machine learning, and we were to think about two areas we might want to be able to address, one would be incorporating physics into these models, so physics-aware or physics-informed machine learning, and the other might be trying to understand how to incorporate empirical information into these models. So those are the two examples I'll give in the next couple slides. So the first example is domain awareness through physics, through being able to build in physics information into machine learning. This is based out of a DOE Oscar-funded consortium or collaboratory called FILMS for physics-informed learning machines. It's led by George Karniadakis from Brown and co-led by Alex Tartakovsky from PNNL. It also involves participation from Stanford, Sandia, UC Santa Barbara, MIT, and numerous other collaborators outside of the basic consortium. So it's a very large effort. Now, the basic idea of the effort is to understand where you have a physical model, what are the best ways, and there's no single way, but what are the best ways to incorporate physical information into these models? In some sense, it's exploring the intersection of data-driven machine learning, which can help you get new insight into systems where you may have had an incorrect view of the model, you may have misunderstood the system, you may have had a poorly formed model or a poorly parameterized model, and combining that with the physics-based modeling that we all know and love from scientific computing and related areas. In some sense, this is an easier road to head down because much of machine learning relies on optimization. Much of machine learning relies on minimizing some sort of loss associated with the system. However, much of our physical systems involve enforcing a constraint, so avoiding violating that constraint and imposing penalties on the violation of that constraint. They involve minimizing some sort of free energy or action of the system. So you can start to get a feeling that maybe the optimization-based approach associated with data-driven machine learning and the way we think about minimization and variation in physical models have a natural fit. And that's what George and Alex and their collaborators have done. They focused on how to include physical information into generative models like GANs to basically be able to reproduce both observations as well as the physical conservation laws or variational principles that one might expect from in these systems. So physical information is still encoded in the form of constraints. Mass is not allowed to disappear unless it's an open system, so on and so forth. Those are built into the systems alongside the learning from the observation that's entered into the system. And it can be shown, as they demonstrated in this plot to the right here, that in fact, incorporating this into the system not only gives you better behavior, you've built in the constraints you don't want the system to violate, you don't want the system to lose mass, you don't want negative densities, so you get that benefit. But additionally, in training, there is a significant reduction in the amount of data that's required to obtain the same accuracy. So it's a very exciting approach. This was highlighted in a paper that was submitted to supercomputing, and I think ended up as a Gordon Bell finalist. Unfortunately, the talk for this from Prabhat, I believe, was Saturday, but this was a multi-institution collaboration. I've listed the institutions here at the bottom. multiple national labs, academia, industry, came together to try to apply this approach to a very local problem for us, and that's the Hanford Nuclear Reservation. So they used it to take observations about, in this case, hydraulic behavior under the Hanford site in the presence of very imperfect knowledge. It's impossible to completely characterize a subsurface environment. There will always be uncertainty. There will always be a limited number of observations. On the other hand, some of the basic rules that you expect for the system, that mass is conserved, that flux obeys particular constraints, those are still very much in play. So they showed, and this is a little map of the Hanford site over here, how to use generative models with physical constraints built in to simultaneously represent and predict the permeability of the system, as well as some of the transport properties of the underlying water levels of the system. And they did so in an extremely scalable way that they demonstrated on Summit with very high efficiency. So if you didn't have an opportunity to hear Prabhat's talk on Saturday, hopefully you can either visit the archive article or catch up with some of the authors. I know several of them are here at Supercomputing. So the second area I want to talk about in domain machine learning is the flip side of the physical problem. Physics is great. Most of scientific computing is built on different forms of physical models that we can turn into high efficiency solvers to get the answers we want. But not all of the world is captured in terms of physical models. And there's a huge amount of problem space, especially in biology, in medicine, in social interactions, in things like the power grid that have a very significant human component, where physical models are hard to apply. And that's where empirical knowledge comes in. So the next project was funded on internal funds at PNNL. It was led by Khushbu Agarwal, Sutane Chowdhury, and Robert Ryo, with collaboration with Stanford and UMass Amherst. And they turned to a place where empirical knowledge has been spelled out in a great level of detail, and that's in the biomedical informatics domain. There are resources like SNOMED and other tools out there that represent knowledge graphs, in some cases fairly complete ontologies of a domain. And these have been designed to help annotate medical records, to do basic reasoning and inference, but they represent a codified collection of the knowledge, the empirical knowledge in these systems that allow, that have been used for many decades and have allowed some efficiency, standardization, and logical operations on an otherwise more or less empirically driven problem domain. So in this case, they wanted to understand how do they build SNOMED into, or SNOMED-like knowledge into the types of machine learning tools that might be used to predict things like patient outcome. So by themselves, you could imagine taking a collection of patient health records, using an LSTM or similar model, and simply trying to drive prediction of patient outcomes based on that. The problem is that there's insufficient data, there is insufficiently annotated data, and there's a question about interpretability, all of which I described in the PRDs, in the priority research directions, that plague just applying an LSTM to try to make progress in this area. But what if you could think about building in all of that empirical knowledge from SNOMED and related ontologies? And that's exactly what they did. They went through and they built in the SNOMED information, which is essentially a large graph, a large directed graph. And with that large directed graph, they came up with different embedding techniques. So some of these embedding techniques would map walk distance between nodes to turn a graph and the relationship between concepts in a graph into a vector. Some of them use somewhat fancier embedding techniques, nonlinear embedding techniques like the Poincare approach. And overall, they showed that they could take the relationship between SNOMED concepts, put them into a vector space, and once they had it into a vector space, start to integrate it into the same type of tools that they would use to predict, to perform more traditional machine learning approaches. And it worked very well. So over here, there's the node to vec, metapath to vec, and Poincare approaches. Those are all the different ways in which the SNOMED information was embedded into a vector form. And you can see that there's a few sanity checks up here to show that it preserves notions of concept similarity and the relationship between concepts in the knowledge graph. In other words, checking to make sure that the knowledge was represented correctly. But then when applied to patient state prediction, these techniques did better or as well as more traditional approaches for predicting the outcomes. So this is a first result in this area. There's a lot more work to do. There are other approaches out there that have also underway from other groups to try to understand how to combine empirical knowledge and data-driven approaches in machine learning. But I think this is an exciting way to now balance the other half of the domain awareness problem, the physics-based domain-aware machine learning, as well as machine learning based on more empirical domain knowledge. Okay, I want to switch gears now and talk about a third example, and this focuses on the inner loop, outer loop issues. So this problem builds off of some of the computational chemistry work that's gone on at PNNL for many decades, exploring complex energy landscapes. In this case, complex energy landscapes of water systems. Water is extremely complicated. It's a very strange molecule. It's the reason why we're all here, but it's still very difficult to predict. And water tends to behave differently based on the number of neighbors it has around, ranging from a few small water molecules in a subdroplet to bulk water. Understanding that is an example of trying to use machine learning to explore and drive the sort of search and minimization of problems in a high-dimensional, noisy energy landscape. And so that's what's happened here. So it's very difficult to list everybody on this slide and stay within my time limits. It was not only a large PNNL team led by Sotiris Xanthias and Sutane Chowdhury and Malachi Shram. It was also part of the broader Exalearn project under the Exascale computing project, for which Frank Alexander at Brookhaven is the PI. Very much a team effort. So the overall effort for this portion of Exalearn is trying to develop reinforcement learning frameworks for physical problems. This specific example shows how to use those reinforcement learning approaches excuse me, to explore water networks and water landscapes. So in this case, they used an existing tool out there, and this was very important, something called SC19. It's a continuous filter convolutional neural network that does a couple of important things, not least of which is address some of the robustness and domain knowledge problems I mentioned earlier in the talk. Water needs to behave in a robust way with respect to translation, with respect to rotation, with respect to change of its internal degrees of freedom. Without that, not only does the search space become a lot more complicated, but you open up the door for some very strange, unphysical behavior. So this is a great example of building a model that respects things that you already know about the domain, and in doing so, increasing the robustness of the overall system. And this was work that was done by another group and published actually in both in NeurIPS, but also in a student thesis. So they applied this to a fairly sophisticated water molecule, something called a Tolle-type polarizable molecule. It's a little bit better than the standard non-polarizable approaches out there for water models. That makes it a little more expensive, but it's a lot less expensive than doing a full quantum mechanical representation. They took a database of about 5 million structures, and they used this to build what's called a physical surrogate. So in this case, the real surrogate would have been the Tolle model and the molecular dynamics simulations and optimizations that went in to understand energies in the system. In this case, they built a more efficient machine learning-based surrogate to try to very quickly evaluate energies with an accuracy that would be similar to the energy you would get out of a molecular mechanics calculation, but a lot less expensive. And that's the accuracy that we're talking about here. Given that, they can then use that physical surrogate in a broader context. This now becomes more of if the physical surrogate is the inner loop part of the problem, the broader context is in an outer loop part of the problem, trying to use a reinforcement learning approach to drive smart search of the environment. So many of you are probably familiar with traditional Monte Carlo searches and similar types of annealing strategies to find optima and explore energy landscapes. In this case, they're using reinforcement learning to try to speed up that search, to make it more efficient. So this is a great example of using a technique like this to empower fast exploration of the energy landscape, while using an inner loop, an inner tool based on machine learning as well, to simplify the very expensive and very complicated calculation of energies. So I'm going to give short shrift in the last example. I had expected I might run out of time. It looks like I'm getting fairly close. And I want to leave time at the end to talk about the artificial intelligence town halls. But DoD, in the form of DITRA and DARPA, have also made significant investments in PNNL, trying to get at different approaches to the interpretability problem. Now, earlier I mentioned the domain-aware machine learning, and certainly many of the ways in which you build domain knowledge into a machine learning model can also be used to get a handle on how that model is behaving, to try to understand which features are important and how it connects to things you understand already about the system. But in some cases, our models are not just imperfect, they might be wrong. And when the models are wrong, we have to start looking for other ways to understand how the machine learning algorithm is working so that we can get some insight, either for troubleshooting or for expanding our overall knowledge about the problem. So I have two probably unreadable, and that's somewhat intentional, slides up here that show DoD, DARPA, and DITRA investments into this at PNNL. And this is a set of work that's been led by very talented earlier career researchers, Svetlana Volkova and Dustin Arendt, along with an experienced researcher, Mark Reeves. And they've used multiple approaches to try to get at the problem of, you could almost think of it as a top-down approach to understanding what's going on inside a deep learning or other very complicated machine learning model. The first uses sort of interpretability by examples. This is this escape route run here on the top right. It uses examples to try to help the user make sense of what's going on in terms of this complicated network by providing the most relevant examples to either different outcomes or different portions of the network. And then the one at the bottom uses model comparison and embedding between models to also try to help user understanding of what's going on in these complex systems. So I apologize, I'm not able to go into this one in much more detail. I've got two remaining slides that have relevant content and then some acknowledgement slides at the back. Both of these slides I borrowed from Steve Lee, Ben Brown, and the great team that put on the recent AI for Science town halls, and that includes Steve and Ben, as well as Rick Stevens, Kathy Yellick, Jeff Nichols, and Barb Helen. So there's a series of these town halls that were held recently. As you can see, there's very broad participation across the country, and this is continuing the discussion of what it means to bring AI and machine learning into the everyday discussion and application in scientific computing. There will be reports coming out, and there's a lot more coverage of this elsewhere, so I'm not going to go into a lot of detail here, other than to make you aware that these took place. And I took this slide from Steve and Ben, because it gives a really nice sort of, almost like an inspirational closing to my talk that also tees up what's next through these AI town halls. So this is some of the vision of over the next 10 years what AI will let the community do in science, and it was a direct result of these town halls. And you can see that many of the exciting things outlined here, a lot of the promise of AI and ML also ties into those priority research directions that I described earlier in the talk. We're probably not going to have one without the other. And so in order to realize this vision over the next decade of what AI and ML can do for science, we're going to have to make progress on those research directions as well. We're going to have to fill those gaps, addressing the problems of domain awareness, interpretability, robustness, learning in data-intensive and noisy environments, and the idea of how to optimally use machine learning in an inner and outer loop capacity in scientific problems. So I want to wrap up by saying that, again, most of this work wasn't mine. I'm just kind of the talking head that's up here describing it to all of you. It's very much been a community effort from the start. Scientific machine learning itself is not new. It's been around for a long time, but there's some urgent things we need to do in order to put it in its rightful place alongside scientific computing and scientific data management. So that's it. I will leave you with this also probably unreadable slide, which was my attempt to inventory what's going on with AI and machine learning through the DOE labs at supercomputing. And I think this slide might be on the web somewhere as well. If it is, hopefully you'll you look for it. Otherwise, I found you can go to the SC19 tool, search for National Lab. You'll find most of this already. But the point here is to illustrate the national labs and DOE are heavily invested in this area. We all see the promise and the excitement of what can happen when we bring AI and ML to scientific discovery. So thank you.
Thank you very much. So a very insightful talk. So I think we can take a couple of questions. Either if you have any question, please come up front to the. Oh, please, number 4. Go ahead.
Hi, thanks for the really interesting talk. I got a very quick question. So you showed several examples of, well, you showed one example of using finite elements in engineering. And that's an area where people spend considerable amount of time actually building the model. So building the geometry, applying loads and so forth, applying boundary conditions, and then they do this over and over again. And that's a very sort of human-intensive, very repetitive kind of thing. Are you aware of any machine learning approaches in that particular area?
Just to clarify, for the problem of avoiding issues in adaptive meshing, is that? Okay. So that example was from Livermore, so I have to turn you over to Jeff Hedinger and folks like that for the details. But I think this is a great example of why, where AI can play a big role or where ML can play a big role. So if you look at moving mesh methods, and that's where these methods are popping up in particular, tracking a front and adapting the mesh to follow a front, you're absolutely right. It obeys a set of laws. It obeys a set of rules. You can respect element volume and things like that. But those are very expensive rules to enforce. And those are very expensive and nonlinear systems to evaluate. So this was designed to really help increase the robustness, either with respect to time step or how the meshing was being carried out. So I think it's a great example that gets at a lot of what you're saying. It's not that we don't know how to preserve a good mesh as it's evolving through time. It's just that it's very expensive and it goes wrong a lot. And so it's an opportunity for ML to be used to kind of correct and improve how that process is carried out.
All right. Okay. So number 3, go ahead.
So thank you for a very nice talk. You mentioned those science ML town halls, and I was wondering if they are all finished or if they are still happening somewhere, or if there is, opportunity for people that missed them to contribute somewhat.
So my understanding is that the initial round of town halls is complete. They're in the process of writing up the results for those. However, my experience with DOE and with Oscar has been that they're always happy to hear good ideas and they're always happy to get others' input. So as I mentioned, Steve Lee has kind of been my primary point of contact for all things Oscar and machine learning. There's also a new AI technology office out of DOE that's fielding a lot of the issues with coordination and such. So both of those would be good ways to follow up on the activities of the town hall.
Thanks.
Okay, so I want to conclude this session, and this is a small gift from the general chair of this SC19.
Thank you.
So yeah, let's join me to thank again Dr. Baker.
Thank you.